Hi, my name is Manish Gupta, and in this video, I'm going to talk about our recent work on enhancing tail performance in extreme classification by label variance reduction. This work is going to be presented at ICLR 2024, and this work is in collaboration with Anirudh, Rahul, Jatin, Bhavna, Mudit, Neelab, Deepesh, Vidit, Sonu, Yash, Ram, and Manik. So let's get started. All at Microsoft, right? So let's get started. So let me first talk about extreme classification. So recall that extreme classification is the problem where a data point needs to be mapped to a subset of relevant labels from a very large label space. So you may have a problem setting where there are like millions of labels and you want to map a data point to a few selected subset of those labels. Now, extreme classification by itself is a challenging problem, but what is even more challenging is extreme classification for tail labels, specifically because, so what are tail labels? Labels for which there are not enough data points, very few number of data points. Now, this leads to classifier overfitting for those particular tail labels, and also there is a missing label bias. So if there are missing labels for some data points, then that makes this problem even worse. Okay. Now, a tail performance in extreme classification could also suffer because of this another kind of a factor called as label variance, which has not been studied earlier, which is what is the focus in this paper. So what is label variance is the question then. So label variance, in simple words, is inaccuracies or mistakes in ground truth when a complex distribution of label relevance is sort of approximated in a heuristic manner with some discrete subsets of labels for each data point. Yeah, which basically means sometimes there could be missing labels, which also means that sometimes there could be incorrect labels and so on. Okay, let me give you an example. So let's take the example, extreme classification problem example of item recommendation to users. So basically, there is a particular user and you want to basically figure out which of the million items on Amazon should you recommend to this user. Now, of course, one way of doing this is based on click feedback. So we basically look at what this user has clicked. We use some recommendation system algorithms and do that, or essentially look at the click feedback, use that as golden labels, and then learn extreme classification mechanism on top of that. However, the problem is that feedback in form of user clicks is subject to variability as a user's interests change over time, right? So what I like now may not be things that I would prefer to buy like 2 years, 5 years down the line. Okay. So this click-based ground truth collected within a finite time frame may also not be entirely accurate. So sometimes maybe I like something, but if it's just that we got those clicks in 5 months, and in these 5 months time period, I did not buy it or I did not click on it. So that doesn't mean I dislike it. So which basically means there could be missing labels, there could be inaccurate labels because of change in interest over time and so on. Now, this is what is called as label variance problem. And here, what I like to buy on Amazon is a very complex distribution, and I've approximated using click behavior, which leads to label variance. Okay. So it can also occur in datasets with expert annotation due to differences in relevance judgments among experts, and which is a very common problem, right? Several times you get annotations done from experts, and then there are, subjectivity, and therefore there are differences in their relevance judgments. It could also occur because of approximation of large-scale data tasks through a finite training sample set. So wherever there are samples, you could always have a label variance problem. In some cases, it is very prominent, but in some cases, it could be very small. Okay. Now, previously, several efforts have been done to improve tail performance in extreme classification, mainly geared towards how to avoid the overfitting of one versus all classifiers. Okay. So these techniques include regularization, handling bias, or also basically handling data scarcity in tail labels. Okay. So of course, if there is overfitting going on, regularization is a very, very obvious technique. And there are methods like ProXML and GLASS, which basically employ a L1 regularizer or a label correlation based regularizer so as to avoid this overfitting. Yeah. Bias could also be there because of missing labels. So, and therefore, one way of handling bias is to estimate the missing propensities for labels first, and then recalibrating the loss through simple weighing. So people have done those kinds of things as well. Uh, Data scarcity. So of course, tail performance is challenging because of data scarcity issues in tail labels, and people have therefore tried to augment more data for the tail so as to avoid this problem. So these data augmentation techniques like T-aug and Gandalf are the ones that have been proposed in the literature. But as we'll see, our method is actually better than these data augmentation techniques. Okay. Uh, Some people have also tried to exploit label side features to improve tail performance. So, if the classifiers, if the certain classes do not have enough data points, no problem. If you have very good description about that class category, right? So in that case, you can actually look at the class category labeled text and then build label side features based on that. Okay. So for example, Endgame and Renee are those two methods which leverage label correlations via Siamese encoder architecture and semantically align similar labels in an embedding space. So similar based on their label text and so on. Okay, so that is how they sort of deal with a small number of data points associated with these tail labels. Okay. So in this particular paper, we propose a new method called as lever, which stands for label variance reduction. And the goal is to be able to deal with the variance aspect of the tail labels in extreme classification. Okay. So the way label, so in this slide, I'll explain how lever works, right? So typically in extreme classification, the optimization seeks to do the following, right? It basically wants to discover those classifiers W such that the average loss over all the data points, over all the test data points is minimized, right? Average loss over all the test data points is minimized. So here the classifier is W, which are to be trained, and there is one classifier per label. And each classifier W is more like a weight vector in that senses. Xi is the ith data point, Yi is the label associated with the ith data point. Okay, so or the subset of labels associated with the ith data point. Now, what you want to do is to, of course, minimize this loss. And this loss could be, any kind of loss. So for example, it could be a logistic loss, popularly a logistic loss. It could also be a hinge loss and so on. Okay. So as you see here, this is for the positive labels, this is for the negative labels. The loss part for the negative labels, sort of just expanded version form of this. So the loss function, right? If it's an imbalance kind of situation, you have class weight. So therefore, you have the C to ensure there is a good balance between the positive and the negative relevance and irrelevance of a label for a particular data point X, right? So now the way the lever tries to solve this problem is to, of course, augment the data. So lever also tries to augment the data, the original data set, so that for tail labels, you essentially have more data points. Okay. But the way lever does it is basically takes the original optimization function, but also sort of augments this extra data. So rather than just considering these n data points, now you have more such data points where the actual label is not. So the actual label is not provided by the human or provided as part of the data set, but this actual label comes from a teacher distribution. So the interesting point is you can think about this augmentation that is done in lever as some sort of a knowledge distillation. So basically, given a particular data instance, you can actually ask the teacher to give a particular label distribution or label probability. And these relevance estimates, which are outputted by the teacher model PI hat, are the ones which are used as additional data point so as to define the optimization in lever. Okay. Now, this teacher could also be trained using, in this paper, at least we study Siamese trained teachers because they have been shown to be really good in the literature for extreme classification. Right? And the loss function, basically, which is used to train the Siamese network, is essentially the log logistic loss, or logistic loss in that sense. Right? So that's that. So in short, what does lever do? It reduces label variance by effectively utilizing tail robust teacher model. So it sort of has a teacher model, and from the teacher model, you essentially get the relevance estimates, and you augment that relevance estimate based data as part of the training data so as to train your lever model. Right? Knowledge distillation enhances the tail performance in extreme classifiers, and lever incorporates label, and label document correlations based on a Siamese teacher's embeddings. So this relevance estimate is basically a correlation value between a document and the label, basically the input and the label, or label, as we'll see. We'll double click on this on the next slide, but it sort of gets this extra data so as to do better training. Okay. Now, how is this lever augmented data created, right? So as I mentioned, essentially you do augmentation with this extra term, which is basically extra data, so as to do the training better. Okay. So how is this lever augmented data set created? Well, the first step, so you have, of course, n data points and you have L labels. So the first step that you do is to add each label as a document also. So as a data, on the document side, so there's a document side and you want to classify them into a few labels, right? So what you do is to first step, add the labels themselves as documents, and then the idea is that a label is surely, as a document, is surely relevant to the label on the label side, right? Encoder embeddings are then utilized. So which encoder? Well, it's some Siamese encoder. So if you have looked at the endgame video, you would basically consider the first module M1 as the encoder embeddings, right? So encoder embeddings are then utilized to utilized to pool the label and doc embeddings together. So you basically get encoder embeddings for each document and also for each label. Now, for each label, you're basically going to select the nearest points from the pool and add as ground truth. So you're basically going to say that, hey, for each label, essentially, what I would do is to basically get the nearest document in this Siamese encoder space and add it as extra label. Tau equal to 1 is not necessary. You can actually have like larger number of labels being sampled for specifically for tail labels. Okay. Now, this leads to additional label pairs, of course, right? Because if you think about this as a bipartite graph, you have documents, you have labels, and now it is so it is n plus L now because well, you have expanded, so it is n plus L cross L in that senses. Cross L. So, what you could therefore do is to essentially either add extra links in this n cross L matrix or in this L cross L matrix, and whichever of these two. Okay. So Siamese training was sort of conducted over many batches. So when you have created this augmented data set, right, you have to of course do Siamese training on top now with this particular data set so as to minimize this loss function. Okay. Siamese training was sort of conducted over many batches of labels to give more importance to tail labels. Now, if you think about it, typically when people do when people do this training, they create many batches out of the documents, okay, on the document side. But in this particular case, Siamese training was done such that you do batching over the labels so that you actually give more importance to the tail labels. Okay, just like Endgame or Renee. Even in this case, the Distilbert 6-layer model was used as the encoder. Now, even here, when you're adding this, you want to be sure that you're not adding noise. So it's not like you added all nearest points as extra labels, but you ensure that you add a point only if the similarity is greater than 0.8 with the target label using the in-game encoder embeddings. Right? Lambda was set to 0.5. So which lambda? This lambda. So essentially, how much importance do you give to the original actual labels in the ground truth versus the labels discovered using Siamese encoder embedding cosine similarity? Okay. So experiments were conducted on several datasets, 3 full text datasets, Amazon, Wiki, and WikiC also, 2 short text datasets, Amazon titles, and the 131K and the 1.3 million number of labels kind of datasets. Then the data, experiments are also conducted on proprietary query to keyword matching dataset. We call it QK 20 million with, of course, 20 million labels. Okay. Now, so far, all the datasets in public domain have been all single intent datasets. So, for example, in Amazon titles, if somebody says clothing for men as input, they're expecting those products to be sort of linked to this title, which is about formal shirts for men or casual shirts for men and so on. So the intent is super clear, right? But as you see, more and more use cases have multi-intent kind of thinking, and many times the query or the input is actually ambiguous in nature. And therefore, in this work, we also propose 2 new data sets, AOL and wiki hierarchy. Okay. So what is multi-intent thing? So for example, if you look at query auto-completion task, if a user has typed FACE, after that they could type literally Facebook or face wash, right? So both of them are equally possible. So therefore, we propose 2 new data sets to take care of these multi-intent kind of scenarios. LF AOL 270K, of course, with 270K labels, and wiki hierarchy with 1 million labels. Okay. In AOL task, it is query auto-completion task, and the aim is to match prefix with suffix. So input is prefix, and the label side there are suffixes. In wiki hierarchy, the aim is to match a Wikipedia page to any of the wiki hierarchy. The idea is to match basically an entity to a hierarchy. So essentially taxonomy completion task of matching a Wikipedia category to its parent category. So if you have a Wikipedia category and you want to basically match it to any of the parent categories, and of course several of these parent categories are applicable as possible labels. Okay, so how does liver perform? So liver can, to evaluate how liver performs, We evaluate on several datasets as you see here. So these are the results on 6 different datasets that you see. Right. We evaluate liver. Liver is a generic methodology, so you can actually apply it to various kinds of extreme classification methods. So we apply it to Elias, to Cascade XML, to Renee, right, across these datasets. And we evaluate in terms of various metrics, precision and PSP. Remember, PSP sort of cares about the tail as well, and P is precision, right? So that's that. And evaluated P at 1, P at 3, P at 5, and so on, which is standard in extreme classification literature. So we observe that lever, when applied to any of these methods, actually leads to improvements in performance in most of the data sets that you see here, right? On average, it leads to a PSP increase of about 5.3%, precision increase of about 1.4%, and a coverage increase, which is not shown here, of about 6.5%. In fact, Renee is the state of the art in terms of extreme classification. And what is observed is that Renee plus liver sort of leads new state of the art in that sense, is with a PSP boost of up to 5.5% gain across datasets. Okay. It's highly effective on small datasets. So if you basically look at LF Amazon titles 131K, and LF Amazon 131K, it actually leads to better improvements, even better improvements compared to on larger datasets. And that is sort of obvious because on larger datasets, you do not have the sparsity problem as much and the variance problem as much. And therefore, on smaller datasets, liver is shown to be much more effective. Okay, so if you compare liver with other tail extreme classification approaches, how does it perform? So remember I talked about approaches which do regularization or approaches which basically do augmentation like T-aug and Gandalf. Okay, so liver outperforms regularization and augmentation methods by 4% in coverage and 3% in PSP. So you see the coverage and PSP are being plotted here for 4 different data sets. And as you observe here, Renee plus liver essentially many times basically leads to much better results compared to any other augmentation or regularization methods. Okay, so Glass and Gandalf are also augmentation methods. They also augment data, but they perform in the original label space. So they actually look at label correlations only. They don't look at correlations in the Siamese encoder embeddings for those labels. Okay. Now, this is a little bit of a problem because if your original labels are themselves screwed up, then label correlations at them are going to be screwed up further, right? So highly skewed data sets lack ground truth data for tail labels, and therefore your label correlations is not a great idea to augment your data. Okay. Multi-intent data sets, well, labels may be associated with co-occurring labels of divergent intents. And then if you're basically just using them to figure out label correlations, that causes a lot of noise in the augmented data set itself. And that is why we feel that liver is much better an augmentation technique compared to Glass or Gandalf. Okay. So in comparison, so if you compare with the Siamese teacher, so essentially in this experiment, what we did was to essentially compare endgame encoder with Renee and with Renee plus liver. Okay, so remember, endgame encoder is just the encoder. Renee is a classifier on top of encoder in that sense. So it's a classifier. It is a one versus all classifier. And Renee plus liver is basically a classifier plus this variance handling mechanism, right? So what is observed is that across all of these 4 data sets, Renee improves the precision over Siamese trained endgame encoder, but can actually lose on PSP and coverage. So typically it has been observed in extreme classification that while classifiers are better on the head, encoders sometimes could be better on the tail, right? So therefore PSP could be lower for classifiers themselves, Renee itself. But when you combine Renee with liver, it improves both on the head as well as on the tail because it retains that goodness of the classifiers being really good compared to encoder on the head, and it also improves on the disadvantage that classifiers have on the tail by augmenting interesting instances. So liver therefore improves on Renee both in PSP and coverage while retaining comparable precision. So therefore Renee plus liver is actually better than Renee and better than endgame encoder. So one could also say that, hey, by the way, as you said, encoder is better on tail, classifier is better on head. Why not do an ensemble of encoder and classifier? Is that better than Renee, right? So an ensemble model here basically uses predictions from one versus all classifier model for head labels and encoder predictions for the tail labels. Of course, we are comparing this with Renee plus liver across 4 different data sets. And as you observe, liver outperforms the ensemble consistently on all metrics for 3 of those 4 data sets. So Renee plus liver is actually better than an ensemble of classifier and encoder. Lastly, how about the training cost for liver, right? So So remember, liver does not bring in any inference level costs. At inference time, of course, you have the same model, so you don't basically incur any inference extra costs, right? Renee only brings in training time modifications, and therefore, at train time, yes, the training time actually increases by 3x, and in the worst case, it actually increases by 9x also. So as you can see across different data sets, Renee, by itself takes this time. This is V100 GPU hours, while Renee plus liver can actually take this kind of extra time. If you combine it with Elias plus liver, yes, it's about 3x. Cascade plus liver, it's about 4.86x. Sometimes in the worst case, it could be about 9x. But yeah, I mean, training cost is about on average 3x. But if you look at the accuracy at the test time, at inference time, it's great. And inference, no new costs are involved. So that's that. Okay. So in summary, in this work, I presented liver. Liver leverages a tail-robust Siamese teacher model to systematically reduce label variance. We also sort of presented label variance as an important factor which hurts label, XC performance. So performance for tail labels in extreme classification, and then therefore proposed liver as a way to handle the label variance problem. As observed empirically, a liver can enhance tail performance by about 5% and 6% points in PSP and coverage when integrated with leading extreme classifiers. And therefore, when it is combined with Renee classifier, it sort of establishes a state of the art across several of the data sets. Okay, that's it for this video. Thank you for watching. Hope you liked the video. Connect with me on my LinkedIn or look at my research on my homepage. Thank you.